Okay, so we're going to be doing a video outside of class now. So this is going to be for the data reduction for the very first lab. Okay, so I'm doing this video instead of in class because it's going to be kind of long. Some of you might know MATLAB pretty well and you don't need to stick around for that. Some of you are probably terrified of MATLAB, and hopefully that's not the case, but that's probably true. And you know, you're going to want to go back to this video and kind of scroll through it a lot of times. And by doing this outside of class, I can go a little more in depth than I can go in class just because of time constraints. Alright, so I'm in MATLAB right now. Okay, so I know it looks a little bit weird, but trust me, this is MATLAB, so I'm just doing it in here because it's less cluttered. You can see all of the text that I have, and we don't need to be using the ugly-ass MATLAB GUI that takes up a lot of space for some of the toolbars and stuff. I hate it. So we're going to be doing it in here, but again, this is MATLAB, don't worry. So the data that I'm going to be using is data from one of the groups in my Thursday class, group 2. I'm not using their data for any specific reason. They just have data for every single run, and that's really it, okay? But you can use data for your group if you have all of the data for the first lab. I don't care which data you actually use for the data reduction. And I really care that you did the experiment in person and that you can understand how we do this data reduction and you understand what's going on so you can explain things in your memo. Alright, so first thing we're going to be doing is importing our data. So actually before that, you see up here I typed in clear and CLC. That is important. So I just ran my script, and over here on the right hand side, this is actually my command window. I'm going to put that on the bottom here. So let's say that we have some stuff in our command window here, like A equals 2, okay? Or we have B equals 4. So these are stored now in our workspace, A and B. You see our workspace right here. Let's do... I don't want to be blinded on the left-hand side there, so let's make that dark. Thank you. Okay, so again, A and B, they're in our workspace, and we don't want that. Let's say, you know, we open up a new script, and we don't want this stuff in the workspace anymore. You know, maybe we're defining some new variables in here called A and B, but they're assigned different values than what we have already in the workspace. By typing in clear and running our script again, it's going to clear everything out of that workspace, and it allows to load in all of our new variables. And then CLC, what that is going to do is clear any text that we have in our command window. So if I run our script again, you see everything left our workspace and everything left our command window, which is exactly what we wanted to have. So don't worry about this box here. This is my script that I'm going to be referencing. I'll leave my video down here. Tuck it there. Pretty cool though. Okay. So now that we have that, the first thing we're going to do is import our data. Okay. So I'm going to be doing S_1018. This is going to stand for Steel 1018. And we're going to use our read matrix function. Okay, this read matrix function, it's going to take whatever data that we're importing. In this case, it's a text file, and it's going to import it into MATLAB as a matrix. Okay. Group 2, 1018, steel.text. And at the very end, I'm going to put a semicolon, and that's going to suppress our output. So let's run this right now. Oh, I forgot my apostrophe here. Okay, so we run that, and in our workspace, I know it's small, so if you're on a small computer, I'm sorry that the text is so small here. That's probably something I can actually fix, but anyways, that's our matrix that we now imported. So if I open this up, this contains, I'll put this back over here. So this is the matrix that we just imported. It's from our text file. So let's open up that text file. So it's this text file. You know what? Let's go over. Hello, that's OBS. Let's open this up in a spreadsheet document here so we can look at it a bit easier, okay? Data group 2. Okay, comment delimited. Good. Okay, here we go. Alright, so our very first column that we have here is our crosshead, which you see right there. And we don't care about that for our data reduction for this experiment. Second column is our load. We do care about that. Third column is the time. Don't care about that. Fourth column, that is our extensometer data or the deformation data. We do care about that. Okay, so we basically took this entire text document and we imported it into MATLAB as a matrix. Because all of this stuff up here, it's text, it's symbols, and they aren't numbers, MATLAB throws it out. So it says, screw you, you're not a number. I don't want you to be imported into MATLAB. Okay, let's go back here. And that's, again, what you see here. So first column is the crosshead, second, load, third, time, fourth, deformation. Also, you'll see how I imported this. So I first have data, and data is actually a folder that I have. So let me open this up here. I'll put you down here. Let me show you my layout, okay? So on the bottom here, experiment 1, stress strain vid, that is the current editor or script file that we're making right now. And, you know, me personally, I like storing my data in its own folder. So in this case, it's in data. Okay, so that's why I'm telling MATLAB what path to go from where I'm currently at. So I'm currently in this folder here, but I'm in this experiment 1 stress strain folder. And now I'm telling MATLAB up here, hey, go to the data folder, go to group 2, and then 1018 steel.txt. Okay, so we want to do this for our other materials. We have 1045 steel. So let's put that in here, 1045, 45, and then we have aluminum 6061 T6. So what did I call it? Okay, AL 6061 T6, is that correct? Yeah. And let's name this alum, okay, for aluminum. And then the last thing that we're going to import is our geometric data spreadsheet. So let's do read matrix data group 2 and then /geo.xlsx. Again, you can see that right here. And okay, I know my camera went away for a second, so I'm going to open up that geometric data spreadsheet. And here we go. So your spreadsheet, maybe you guys kind of messed with the formatting a bit with your group. So make sure that you kind of take note of the columns that you have your data here. But in this case for group 2, they have the original average diameter in this column here. This is column 5, 1, 2, 3, 4, 5. And then 6, 7, 8, 9. In column 9, they have the average final diameter. So we care about column 5 and column 9. Okay, go back here. Okay, so let's run our script again, and if we open up our workspace, you'll see that we have everything imported, and all of these are matrices. So you see it's whatever number by whatever number, and it says double. Oh, my camera stopped. Okay, let me get my camera back up. Alright, so we have everything imported. The next thing that we're going to do is define our known. So we have a few knowns that we can just go ahead and define right now. By the way, when there's 2% signs, that's when I'm making a section. So, yeah. Okay. So the first known that we're going to define is our initial length. We don't really need to make a variable for this, but I'm just going to. So I'm going to call this init length for initial length. And we're going to set this equal to 2. And this is in units of inches. If I put a percent sign, anything after that percent sign is a comment. So remember that. Hopefully you remember that from when you took MATLAB. So this line, that's a comment. Everything after this percent sign is a comment. This line is a comment, and then the very first line is a comment as well. Alright, next thing we're going to put is the published values for the elastic modulus. Now, you're also going to have to figure out what the published values are for the yield strength and the ultimate tensile strength. So I'm just going to, for this video, I'm just going to show you guys for the elastic modulus, but you have to do it for those other two values as well, or material properties. So the first one, this is going to be for 1018 steel. So 2, 9, 7, and 1, 2, 3, 4, 5 zeros. And then for 1045 steel, we have 2, 9, 1, 2, 3, 4, 5, 6 zeros. And then for aluminum, 60, 61, T6, we have 99, and then 1, 2, 3, 4, 5 zeros. And all of these are in inches of PSI. So let's put a little comment here at the end. This is 1018 steel, 1045 steel, 60, 61, T6 aluminum, and we have inches of PSI. Okay, so you can, look up these values, and when you make your memo, make sure that you cite the sources as well. Oh yeah, so let's run our script again, and let's open up that variable that we just created, or let's type it out in the command window. So if I look at this pub-em for published elastic modulus, this is a 1x3 row vector. So we have one row and we have 3 columns. You can make this a column vector too if you wanted. Doesn't matter. We just want to make this a vector. So I can make this a column vector again if I wanted, just like that. I'm going to leave it as a row vector though, okay? So there we go. And we're going to be using this later on for some of our calculations. Okay, so we have all of our data that we've imported, and now we're just going to get the rows, or rather the columns that we're interested in, which is the load and the deformation. And we're going to take those 2 columns for every material that we have, and we're going to pull them into something called the cell array, just for our own kind of convenience for this data reduction. So yeah, you don't have to do this step, but I would just recommend it, especially if you're not as confident in MATLAB as you maybe once were. So we're going to do this again just for convenience for this data reduction. Alright, making sure I'm still recording. Okay, so let's say organize. We'll say load and deformation data to a cell array. And I'll explain why we're using a cell array in a second and not something like a table or a regular numeric matrix or a multi-dimensional matrix, anything like that. So our first entry in the cell array, so we have D, and then in our curly brackets here we have 1, 1. For a cell array, to denote that it's a cell array and not some regular matrix, we have to use curly brackets. So D 1, 1, this means that this is going to be the first entry in our cell array D. More specifically, it's in row 1 and column 1 for this cell array. And for this, we're going to get S1018, so steel 1018. And again, we want to get all of our data for the load data and the deformation data. Okay, so when we are defining a matrix, or kind of, if we're defining or trying to extract some values within a matrix, in MATLAB, we always do that by rows, comma, columns. So here, this colon, that signifies our rows that we're going to get, and then in these square brackets here, these are the columns that we're going to get. Okay, So before the comma, we have a colon. Again, that means get all of the rows. And then after the comma, we have in square brackets 2, 4, and that means that we're going to get the columns 2 and 4. Also, let's open this up actually. So I'm going to say open D, and this is our cell array here. Again, sorry that the text is kind of small, but if I open this up, you see that this cell array, inside of that cell array, we have a matrix. Okay, so let's go back here. So we have our cell array here, and you see in the first row and the first column, we have a matrix. So I can double click on that, open it up, and our first column is the load, second column is the deformation. So if you're wondering why we have square brackets, if I don't have square brackets and I try to run this, you see that it says index in position 3 exceeds array bound. So this is acting as if we had a multi-dimensional array for Steel 1018. We don't. It was a 2-dimensional array. So, it's for our comma here, the colon, that's our rows, and after that comma, we want to tell MATLAB the columns that we want to import. Because we want to import both columns 2 and 4, we're going to wrap them in square brackets. And then we can actually import both of those columns, which you see here. Okay, so we're going to be doing this also for our other 2 materials. So that's going to be for 1045 steel and for aluminum. So let's just rename these. And that's all we got to do. So we have now 1045 steel and aluminum, and you see that we're staying with our convention here for being in the first row. So D, 1, that's right here. That's 1018 steel, D 1, 2, row 1, column 2, 1045 steel, and D 1, 3, first row, third column, that's the aluminum. Okay, so now why are we using a cell array, right? So let's do length of D 1, 1, and we'll do length of D 1, 2, and length of D 1, 3. So these are the lengths for all of our matrices that we have in our cell array. So that's, again, 1018 steel, 1045 steel, and aluminum. So length meaning the amount of rows that we have. Or another way to think about it is how many data points do we have within this, okay? Or how many times have we collected a data point. So for 1018 steel, we have 948 data points. That's, for our load and deformation. For 1045 steel, we have 701, and for aluminum, we have 1,138. Another way to kind of think about this is aluminum. It's the most ductile, so it's gonna be a longer test. We're gonna have more data points. Then we have 1018 steel is in between for ductility, and then 1045 steel is the least ductile, so it was the fastest test. So all of these are different lengths, and if we have a matrix in MATLAB, so if I open this up, this is a matrix. A matrix, all of the columns that you have, they need to have the same amount of rows, which is what we see. So I can't, delete these and have nothing in these cells, okay? I can't do that, so in this case, it changed to zeros, but we can't have empty cells, and let's say this column here, and cells that have data in this column here. Can't do that. So we have data that's of varying lengths here. So if I want everything kind of in one spot that we can reference quite easily, which is going to help once we start using a for loop real soon here, it's beneficial in that case to use a cell array, because again, I can have all 3 of these matrices for our three materials, which are different lengths, and I can have them in this kind of one centralized location, and it's easier to reference that data once we do a for loop. Alright, so we're almost to our for loop now. which will be kind of the meat and potatoes of this lecture. But before we do that, we're going to calculate the cross-sectional area that we have in the beginning of the test and at the end, so that fracture surface cross-sectional area. Okay, there we go. So I'm going to make this another row vector, and actually it'll be a matrix. Okay, so this will be a matrix, and it's going to contain the cross-sectional area in the beginning for all of our three materials and the cross-sectional area at fracture. So what's the formula for cross-sectional area? Pi divided by 4 times d squared. Okay, so let me type it out first and then I'll explain it. Okay, comma 5 comma 9 and then squared. Okay, so we have pi divided by 4 and then we have times d squared. So pi divided by 4, that's pretty self-explanatory. Then for our diameter, remember we imported our geometric data and we imported this as a matrix called geo, and that's what you see over here. Just seeing if I can easily increase the text size. I can't though. Oh well. So here, remember row or column 5, that is the average original diameter, and column 9 is the average final diameter. So we have pi divided by 4 times d squared, so we're accessing this matrix geo, and I want to get all of the rows in column 5 and all of the rows in column 9. So that's similar to what we did up here for getting both of those two columns. And we have a period, and then a multiplication sign, and a period, and then a square sign, or power sign. Because we're doing an element by element operation. We're not doing matrix multiplication. We're doing kind of, what I would call like everyday multiplication. So we need to do an element by element operation in MATLAB, which is given by a period, and then whatever operation you want to do. So if you need to refresh yourself on that, make sure you go back to your notes for when you took MATLAB and take a look at that, okay? Because that's kind of its own kind of subject in MATLAB. Okay. I'm going to pause this real quick, and then I'll be right back. Okay, so I'm making I wanted to make sure that, I don't lose everything that I record. Okay, here we go. So now we're going to be able to do our for loop now. So we're going to do a for loop so we can just do some of our calculations one time instead of 3 times. So we're going to be doing calculations like for stress, for strain, and the elastic modulus. So, we need to calculate the stress for all 3 materials. I don't want to type out 3 different lines where, each line is for one material. Instead, I can use a for loop, and I can calculate stress for all of those 3 materials just on one line. Okay. So let's make a new section here. Let's call it calculations. Okay, so for a for loop, we're going to do for I equals 1 to 3. You can say for n equals 1 to 3, e, p, m, whatever. It doesn't matter. Okay, I is just our counter variable. So we're going to loop through this. On our first loop, we're going to be at I is equal to 1. Second loop is going to be I equals 2. Third, I equals 3. So the first thing we need to do is delete rows where we have a negative value for load. Delete rows with a negative load value. So there's something that happens when we do our test, our stress strain test, where we apply our load and, eventually it fractures. And after it fractures, though, our machine, it still records, like maybe one value or a few values for the load. And it's recorded as a negative load, which you see here in this column. So we have negative 18 and negative 143. But we don't want that actually to show up in our test. What you would see is like, we fracture, and then it's gonna go down. And we don't want that to happen, because that's our test has already ended once it's fractured. So what you could do is delete these manually, and you would actually need to do that in your script though. So you would need to say, okay, row 947 and 948, I'm going to delete them. But that's not good practice. That's hard coding. If you guys took me in for MATLAB, you know that we usually try to avoid hard coding. For some of the stuff they're doing in here, technically there's hard coding, but either just you can't really avoid it, or we're just going to keep things simple for now. But imagine that instead of having 3 materials, we had like 50, 100, 1,000, whatever. You would not want to go into each kind of matrix and delete all of those rows manually. So you'll see for 1018 steel here, we have the last 2 rows have a negative value for the load. If we open up the one for 1045 steel, it's not the last 2 rows, but this time it's only the last row, and that's the same thing for aluminum. So again, instead of deleting these manually by ourselves, we're going to delete them with the use of code. So we want to loop through each of these matrices that are within our cell array here, and we're going to have MATLAB look through all of those rows, and if it sees a negative value for the load, it's going to delete that entire row, because again, we don't want that. Okay, so I'm going to do this in kind of 2 steps. So it's going to be done on 2 lines, but we could also do this in 1 line if we really want to. But doing it on 2 lines is a bit easier to kind of understand. So the first thing that we're going to do is find when we have a negative value, okay? So how do I want to do this? Let me delete that. I'm going to say find when load value is negative, okay? So I call this neg for negative. Okay, you always want to put your variables as something that makes sense. So neg is equal to d1 comma I. And what this is going to do right now, if we just have this, and we run this, nothing happens. I mean, I did suppress this output, but if I type in neg, this is just going to return basically this entire matrix that we have, okay? And so what it's doing is, on our first loop, we're going to be looking at this matrix, so that's d1 comma 1, okay? On the first loop, I is going to be equal to 1, so neg is equal to d1 comma 1, which is this matrix here. On the second loop, it's going to be, neg is going to be equal to d1 comma 2, so that's going to be this one, and then third loop, this one. But again, we want to find when the load value is negative. So let's open up our first matrix here. Remember, that was the last 2 rows. We see that in this first column we have 2 negative values, okay? So to type this out, we're going to do colon comma 1 and then less than 0. So let's break this up again. d1 comma I in the first loop, where I is going to be equal to 1. So for this part here, d1 comma 1, we're looking at this matrix that I have opened up on the left hand side. And then in parentheses, this is kind of layered array addressing. So we're first looking at our matrix here that you see on the left by typing in d1 comma I. Okay, on the first pass, we're looking at d1 comma 1, so that's right here. And then in parentheses, that's array addressing for that matrix that we're looking at. And in this case, that's all of the rows in the first column. So it's looking at all of these values in this first column, every single value. And then it's checking through this logical or relational operator, rather, less than 0. So our answer is going to be a logical vector, okay? It's going to be a logical vector that says whether or not our number is less than 0. So if I run this now and I open this up, see if I can pull this out right. Not what I wanted, but that's okay. So let's repeat this one more time. So let's just imagine we're in the very first loop here. Actually, let's imagine that we are in the last loop. So I is going to be equal to 3. So now we're looking at d1 comma 3. that's for aluminum here. Let's open that up. And neg, so we're in the third sheet for aluminum, and we're looking at all of the rows in the first column. So all of the rows in this column. And just by looking at this manually, we can see that this last value is negative. So at this less than 0 sign, if we have a value in this first column that is not less than 0, we're going to get a false answer, which is going to be a 0. So that's a logical answer. 0 means false, 1 means true. Okay, so if we're less than 0, or if we're not less than 0, we get a logical answer of 0. And if we are less than 0, we're going to get a logical answer of 1, which is what we see on only this very last row. Because remember, we have a negative load value here. That's less than 0, so we get a logical result of 1. Okay, so that's kind of how we can have MATLAB tell us when we have a negative value or not. And how this is typed here, we're only looking at that very last result for the very last pass. Okay, but the other two passes, the same thing. It showed us what it was, okay? So if I was on the first pass, then we would see a logical answer of 1 for the last 2 rows. Okay, so now we found when we have a load value that's negative. That's good, but now we need to use that knowledge to delete those rows when the load value is negative, that entire row. Okay, so to do this, let's go back up here. We're going to be using array addressing. So we're going to... I might need to sneeze. So we're going to be doing array addressing, where again, we're looking at our cell array D, and all we have so far is just one row. And we want to loop through for each of those columns. So we look at each material. And from here, we're going to use what we just made right here, this logical array basically. We're going to use that as array addressing. So in our parentheses, we're going to type a neg. That's going to represent the row. So a 1, that's going to basically act as array addressing for us. And a 0, nothing's going to happen. And then we're going to put a colon because we want to delete all of the columns for those rows when we have a logical result of 1, meaning true. And we're going to set this equal to empty brackets, which is basically going to delete that row. Okay, so again, let's imagine that we are in the third loop, okay? What this is going to do here, it's going to go into the loop for D1, 3, that's aluminum, and then we're doing array addressing inside of this matrix here. We are acting on the rows for neg, and this is only acted upon when we have a logical result that was true, so that's when we have a 1. So in this case for aluminum, we only have a value of 1 or true on this very last row when we have a negative load value, less than 0. So we are only going to delete this very last row. So if I run this script, you'll see that very last row is going to go away. And there you go, it went away. And so this was also acted upon in our very first matrix here. So now we no longer have those negative values, and same thing for the second one. There's no negative values at the end. Alright, next thing we're going to do is do our calculations now. So for stress, for strain, and the elastic modulus. So we have a cell array over here. In the first row, that's our raw data that we have for each material. And for our second row, I'm going to put in all of the stress calculations that we're going to have now for each material. So if I want to do this for the second row, I'm going to do D2, I. And this is going to create a second row, and then for each column for I, we're going to add each material that we have. So our stress formula is very simple. That's just going to be load divided by the cross-sectional area. And remember, we're doing engineering stress, so that's the cross-sectional area in the beginning. So let's first type in our load. That's going to be D, 1 comma I, and we're looking at, not that, it should be 1. And we're looking at all of the values in our first column. So remember, let's pretend we're on the first loop again. We are going in D, 1 comma 1, so that's for 1018 steel. And then inside of this, we're doing array addressing to get all of the rows in our first column, which is for load. Okay, so this is our load for 1018 steel if we're on the very first pass. And we're going to be doing element by element division. We need to divide this by the cross-sectional area for our given material, the original cross-sectional area. So we have, not D, we have area, okay? And this is going to be 1. Let's actually open this up. I'm doing this a little different than I did in my class earlier today. So open area. So for our first material, and actually to go through all materials, we're going to do, this will be area I, comma 1. So now, for our first material, that's going to be our first row. Second material is the second row. Third material is the third row. And we want the original cross-sectional area, so that's this first column. There we go. And there we go. So we can run this now, and that runs, and now we have our stress calculation. Okay, so let's open this up. Let's go back to our cell array. That's here, and now we have this whole new second row, and you see that all of the lengths here, they're the same lengths as the corresponding column in the first row. That's because, we're just converting that load data to stress data. Okay, just as we did for stress, we are going to do this for strain. So, strain, and let's make this the third row now in our cell array. And all we have to change is 2, and we're gonna divide this by our initial length. So init length, which we defined earlier up here. And now we can run this, and now we have a third row, and that's the calculations for our strain. So to recap, we're making this third row here, D3 comma I. And then we're looking at the very first row in our cell array, because that's the load and deformation data. And once I go inside the respective matrix for each material, we are going to get all of the rows in the second column. Remember, the second column is deformation. And to calculate strain, that's our deformation divided by the initial length. So divided by the initial length. There we go. Now we got our strain. Next thing is the elastic modulus. So the formula for this is going to be sigma 2 minus sigma 1 all over epsilon 2 minus epsilon 1. So let's open up our lecture notes. Okay. Okay. Being a little dumb here. Let me make this a little bit bigger. Okay, so to calculate the elastic modulus, if you remember in the lecture, I said to choose a wide spread. So we want to choose a value that's, maybe up here for sigma 2 and epsilon 2, and then a value maybe around down here for sigma 1 and epsilon 1, okay? And you want to choose points that are within the elastic range, because, we're calculating the elastic modulus. So we need to be within that elastic range. And we want to have this kind of spread and not have our 2 points, down here or up here or even in the center, although that's probably okay, or it's better in the center. We don't want them super close together because then we're going to introduce the effect of noise in our data. So we want to have a nice spread so we can reduce that effect of noise once again. So I don't want to go exactly at the origin. I want to go a little bit up again, because of noise, there's a little slack in the beginning of our test. I want to make sure that we're past that point. And you want to make sure that you're a fair amount away from when the elastic range ends. So you want to make sure that you're within this linear region somewhere. So don't just blindly copy down what I have here. Actually, take a better look than I did, quite honestly, for these points, okay? And for the Friday classes, you guys have less amount of data points, okay? So the data that I have here is from Thursday. Our data acquisition rate was higher than the classes on Friday. So the links that we have here, like 900, 700, and 1,000, on the Friday class, it's probably a lot less. I'm not sure how many, but it's going to be less than this. So, a value like 200 for Thursday, the 200th row, let's say for 1018 steel, we might be well within the elastic range, which we are. But for Friday, the 200th row for 1018 steel might be in the plastic range already. So, again, you got to pay attention to that. So I'm going to make this our 4th row in our cell array. Okay, I'm just adding new rows all the time. And again, in the numerator, that's going to be sigma 2 minus sigma 1. So that's stress. So that's going to be our 2nd row that we created. That's stress. So D, 2 comma I. We're going to loop through for all of those different materials. And then within this, we're going to be getting the 200th row. Okay, so this is a column vector, so I don't need to have 200 comma something. It's just a vector. So 200 means the 200th value within this vector that we have. In this case, for 1018 steel, that's a load of For 1018 steel, the 200th row is a value of 3,869 pounds. Oh no, I'm looking at stress. I was reading that and realizing I didn't carry it over enough. I want to look at the load rather. Okay. So yes, our formula does have sigma 2 minus sigma 1, but I'm just so we did the lab in person. You guys were looking at the load data throughout. So let's go to the load data for 200. That was 3,573 pounds. Okay. Yep. Okay, there we go. And yeah, that was before the elastic range ended. Okay. So we have sigma 2, and now let's do minus sigma 1. So the 2 comma I, and then I'm going to choose value of 10. So that's going to be our 10th value. And now we need to take this. So I wrapped our numerator, by the way, in parentheses. And now we're going to divide that by the denominator, which is going to be epsilon 2 minus epsilon 1. So d 3 comma I, the 3rd row, that was our strain that we calculated. 200 minus d 3 comma I, and then 10. We run that, and then we get one value for each of our materials, which is going to be the elastic modulus, and that's, remember, in units of psi. Alright, next thing is the percent error. So now we're going to check out what our percent error is for the elastic modulus for each material compared to published values of the elastic modulus. We're going to make this the 5th row. Okay. And we're going to calculate this by getting the absolute value. Make sure you do absolute value because there's no such thing as a negative error. Okay, it's always going to be positive error. So let's get our absolute value. And we're going to get our value, subtract that from the published value, and then divide that by the published value, multiply it by 100 to get a percentage. So d 4 comma I, that's our elastic modulus that we calculated, minus the published elastic modulus. Okay, and then we're going to do divided by the published value for the elastic modulus. Okay, if I can type. pub em I. And we're going to multiply that by 100 again to get a percentage. Okay, let's see. I did something wrong because this is obviously way too high. Okay, so let's see. D 4, 1. Okay. And pub em 1. Okay, so give me a sec, and I'll figure out. I was hoping this wouldn't happen. So I probably just typed something wrong at one point. Let me figure this out, and then I'll be back. Yep. Alright, I was even looking at my other script, couldn't figure it out at first. What I forgot to do was close the numerator here in parentheses. So these parentheses here, I didn't have, and of course that's gonna basically be a different equation that we have. So make sure that's in parentheses. And then if we run it, we get values that are normal. So the percent error for 1018 steel for the elastic modulus is 3.48%. For 1045 steel, 0.95%. And for aluminum, 6061 T6, 0.27 or 0.28%. Really good. Really good. Okay, maybe past semesters, the specimens that we had, they may not have been of as high quality. Yeah, because they're usually higher. So this is really good. Nice. Alright, so that's all of our calculations. Well, at least in our for loop, we still need to do something else, which is finding our yield strength. Okay, remember the old yield strength. Let me open this back up. Okay, so our yield strength, we need to find that when our yield point isn't clearly defined. So you see in this curve here, it's not clearly defined, so we use our offset method to find that yield strength. So to do this, we need to offset our graph to 0.002 inch per inch. And then we draw a line that's parallel to the line of our elastic range. And when this offset line intersects our stress strain curve, that's going to be our yield strength. Alright, so we're going to be doing that now. So I'm just going to do this for one material, which is going to be 1018 steel. But I think you need to do it for the other materials as well. If you see a well-defined yield point, then you don't have to, but from what I remember, none of them are well-defined. So let's make this another section called yield strength. And we're going to be making our parallel line, okay? So let's call this parallel offset line. Actually, let's do parallel offset data for X and Y. Okay, so if we want to plot a curve in MATLAB, we need to supply the X data and the Y data. So for our X data, I'm going to call this offset X. And all I'm doing here is defining I'm defining an X domain or an X range. So from 0.002, that's, where our curve is going to start. And then I'm going to use a step size of 0.001. And we're going to go to a final strain value of 0.006. Offset Y, this is going to be our Y data. This is going to be D4, 1. That's our elastic modulus. And for 1018 steel, then multiply this by offset X minus 0.002. So what the hell is that? The steely-eyed boys or gals in here, you might recognize this. This is just y equals mx plus b. So our slope, remember that's the elastic modulus, rise over run, that's stress over strain. We already calculated that slope, it's the elastic modulus. In this case, we're doing it for 1018 steel, so we have D4, 1, that's m. And then x is our offset x data. So in this case, we don't need to start from 0. There's no point. We're starting at 0.002, and kind of arbitrarily, I'm going to 0.006. You can make this a larger number or maybe even shorter, but you want to make sure that that x range is large enough so this curve that we're going to plot here, this offset curve, is going to pass our stress strain curve at some point. And then we're doing minus 0.002 because we need that offset. Remember, we don't want to plot this at the origin. We want to offset that x-intercept at 0.002 inch per inch for the strain. Okay, so we're going to plot this soon, but that's what we're doing. And now we need to find the intersection point. So to find an intersection point, what do you need? You need two curves. So we have our stress strain curve, which, it's just our stress data and our strain data. And we also have our other curve, which is the offset curve, which we just defined here. So in square brackets, you need to make sure you do that. We're going to put int x and int y. So call it whatever you want, but this stands for the x intersection point and the y intersection point. We need to type in both of these, okay? But all we're really concerned with is the y intersection point, which is going to be the yield strength that is going to be given for our material, okay? So the function that we're using is poly-x, poly-y. And for this, you need the mapping toolbox in MATLAB. Hold on, I'll show you how to install it in a sec. So poly-x, poly-y, that's the function that we need to use to find our intersection point. And the syntax for this is going to be x1, y1, and then x1, y1, and then x2, y2. So again, just our first curve and then our second curve. So for our first curve, let's do x1, that's going to be D3, 1, that's our strain data for 1018 steel. The y data for 1018 steel is D2, 1, that's our strain data. Now let's get our offset x data and then our offset y data. Run that. Int y, this is going to be our yield strength. So there's a bit of plus or minus here. You can get like the average of this, something like that, and that'll be your yield strength that you have. Okay, and we're actually going to plot this soon here, and you will see that this indeed is our yield strength. So how to get the add-on. So let's open up MATLAB. Again, I was in MATLAB, but it was a more kind of trimmed down version. So to get the mapping toolbox add-on, we need to make sure that we're in the home tab here in MATLAB, and we'll click on add-ons. This window is going to pop up. And you might already have the mapping toolbox installed, by the way. And we're going to type in mapping, press enter. And it's the very first option here, mapping toolbox. I already have it installed, but if you don't have it installed, you'll see over here like a download or install option. I don't know what it is. Download it, and then bada bing bada boom, you gotta restart MATLAB. It's going to be installed. Alright, there we go. Go back here. So we have our intersection points. Now let's start doing some plots. So I'm only going to do one plot here. You're going to have to do the other plots by yourself. But it's easy. So I'll make a section for plotting. I always like to put in figure visible and then on or off. So if we have, you're going to have multiple plots. You're going to have 6 plots for your deliverables. And sometimes you don't want them to show up or at all, or maybe you only want 1 or 2 to show up, whatever. So you can start off each figure with this line here, figure visible on, that's going to generate the plot. If we have figure visible off, that's going to suppress the plot. So speaking of the deliverables, guess I'll open this up too. I should have talked about it in class, but if not, here we go. So your deliverables are here. Thank you. So you're going to have 6 curves like I just said. So first thing we need to do is compute the stress and strain. We did that in our script. Plot the stress strain curve over the elastic range is 1 and the entire range is 2. So we have 3 materials. Each material is going to have 2 graphs, so we have 6 graphs in total. So if you're plotting this for just the elastic range, you're going to have to constrain the amount of data that you're plotting. Okay, so I'm going to leave that up to you. Then you got to label some regions of interest. Error analysis, we showed you how to do that for the elastic modulus. You also need to do that for the yield strength and the ultimate tensile strength. Calculate the percent reduction in cross-sectional area. I'm not going to do that just because it's such a simple calculation. You guys can do this in MATLAB. And then the expected sample calculations are down here. So, you're actually going to be typing this out. I'm not going to accept MATLAB code for this. You actually have to type out the symbolic formula and then carry it out. And, for sample calculations, remember, you only need one per thing. So I only need one sample calc for stress. I only need one for strain and so on. Alright, so that's the deliverables. I always close that on accident. Okay. So let's make our plot. So again, I'm doing this for 1018 steel. So let's do our stress strain curve first. So the syntax for this is x comma y. We need our x data. That's going to be our strain data. And then we need our stress data. There we go. And I'll do comma B for blue. And I'm going to make the line width a bit thicker than the default. I'm going to run this now. Thank you. And there we go. Here's our plot. For now, I'm going to comment this part out just so I can run this. And I can leave this figure up open over here. And every time I run the script, it's going to just update the plot. If this line is uncommented and I keep running the script, it's going to generate a whole new figure. It's a little annoying. So there's our stress strain curve. Let's add in some labels here. So X label, we're going to call this strain. This is in inch per inch. Y label is going to be our stress. This is in units of PSI. And then we can add in a title, stress strain curve for 1018 steel. Run that. There we go. This updated. We want to fix this so we don't have these exponents on the y-axis. So to do that, we're going to type in AX equals GCA, which means get current axis. That's going to get all the properties for the axes on this figure. And then we're going to type in ax.y-axis.exponent equals 0. The capitalization for all this does matter. Run it again. The exponents go away. Cool. Now let's kind of show you the proof in the pudding for the offset curve that we made, and we're going to show that we did calculate that yield strength correctly. So first thing, let's plot that offset curve. So if I want more than one curve on a plot, I need to type in hold on. And let's do plot offset x, that's our x data, and then offset y. And let's make this a blue dotted line. I should do a dash dot. I think that's how you do it for a dash dot. Yeah. Line width 2. Looks ugly as hell. Let's do a dotted line. This might look a little prettier on your computer. The graphics on Linux for MATLAB is kind of doo-doo. There we go. So the blue dotted line, that is our offset curve. So that's starting at 0.002 inch per inch. Guess we can just go down here. Okay. Well, there it is. Just run again, so it's reset. There we go. Yep. And let's do one more line here, and this will be a horizontal line for what we calculated for the y intersection point, otherwise known as our yield strength. So let's do y line, because we're starting at that y value, and we're gonna type in int y, and let's make this a black dashed line. And there we go, there's our black dashed line. So remember, we had 3 values that it gave us. You know, I'm zoomed way the hell in here. So you see those 3 dashed lines. You can just take the average and say that's your yield strength. And you can see, again, this was on Thursday. Thursday, you guys had a ton of data points that you collected per second. So you can really see how, yeah, it's not a perfect smooth curve here. There's some noise throughout. And so anyways, at this intersection point, that is our yield strength. And this, you know, this black dashed line, that corresponds to when we crossed over from our offset curve to our stress strain curve. Yep, geez. So yeah, I think we have 3 values here because, yeah, we crossed the stress strain curve. Our offset curve crosses our stress strain curve at 3 different points. So again, just take the average. Alright, there we go. The last thing that you need to do is have some labels. So it's like for the elastic range, the yield strength, UTS, and fracture point. Maybe there's a little more, I don't know. So to do that, you can do 2 different methods, maybe even more, but the easiest one is typing in, let's put it down here, is typing in G text, and then in here, let's say, I don't know, fracture point. Now if I run this, you see that I have crosshairs? Let's go down here. Okay, of course it looks crappy. But there we go, there is our fracture point right there. I could just use those crosshairs to place down where I wanted that. So yeah, you know, there's a benefit that it's easy just to click, but if you're running your script multiple times, that's always going to show up, and that can be a little annoying. So we can use a different function called text, and for this we need to supply our x value and our y value, and then whatever it is that we want to have for the text. Okay, so at least I think that's the syntax. I haven't used it in a while. So for our x value, let's do 0.09. That's for the strain. And then for the y value, I can just quickly figure this out by d2, 1, then end. Okay. 6 point, I'll just say 0.8 e plus 4. There we go. So I ran that, and yep, there it is. There's our fracture point. Let's lower this a little bit. And let me do, I'll do 8.5. So 6.05. It's just, it's overriding what we had. So let's run this again like this. That's pretty close. Let's do 6.025. A little more. 1.5. There we go. That's reasonable. So you get the idea. We can put in the x location and the y location directly, and then specify what we want for the text label. And you can also change the color of this for the label. So I can say color red, and now that label is red. Yeah, that's better. So there we go. That's how you make your labels. And if we want to export this figure, you can do it the usual way. So you're going to go to File, and don't do Save As. Go to File, and then go to Export Setup. We're going to click on Rendering. And then for the resolution, the DPI, we're going to put that at 300. Click on Export. Save it as a PNG. And then save it wherever you want to save it. But we can also save this through code. So you need to make sure that you have AX equals GCA. Okay, I had a little snippet. And the code to export this, to export your figure in code is export graphics. First argument is AX, that's what we defined here. Then we type it for whatever we want to call this. I don't think we can start with a number, so let's do steel 1018 full, because this is the full range, and then you supply the resolution over here. Also your file extension, so I'm doing a .png, 300 dpi, and just to show you that I ain't lying, let's go here. Let's actually make a folder called figures. Okay, I'll go back here and I'll say figures. So I just made this folder. There's nothing in here. Okay, there's nothing in the folder. Let's run this, and you can see that it just kind of popped up real quick. That was MATLAB actually saving the figure, and there it is. And look at that, it looks real nice. Nice quality. I would move this label over or change the X limit here. So let's change the X limit. Okay, now this is starting to go on a little bit. I can also, oh yeah, let's uncomment this and change this to off. Let's do X lim 0 to I don't know, 0.13 maybe. 0.13. Run it. Thank you. Okay, that was too much. 0.12. And let's lower this a bit to 5.8. There we go. And that looks real nice. So now this label isn't going off the figure. And this is nice and low. And this is great quality. Even if I zoom in a lot, it's still pretty good. And yep. Alright. So that's how you do the data reduction for the first lab. If you have any questions on anything, you can ask me and I'll help you. Something I forgot is the UTS. So one of the things you need to also show is the ultimate tensile strength. This is real easy. So all we got to do is the max stress. Okay, so that'll be max. If we're doing it for 1018, this is going to be for D 2,1. UTS 1018. There we go. That's the UTS. Okay, that's it. Hope this helped. And you might watch it a few times just to really, I don't know, remember things. Anyways, it's getting late, so hope you found this useful. We're gonna be doing stuff like this for the rest of the semester. I'm not gonna have videos that are as detailed as this, most likely, but I'll still be helping you guys throughout the semester. Okay, bye bye.